Perfect, perfect, perfect. All right, genetic programming. Again, like everything else we've seen in this course so far, none of what I'm about to say is set in stone. Everything with evolutionary computation is, here's the idea, and then actual specifics for implementation is whatever the hell you want it to be. Do whatever. In fact, again, I encourage the creativity. Try things. I don't care if what you tried end up being a dumb idea. Sometimes you don't know it's a dumb idea until you try it. Maybe in hindsight, you're like, oh yeah, I guess that was dumb because of X, Y, Z. But until you did it, you never really knew. So everything I'm about to say here comes with the asterisk of, this is the idea, and then how you actually implement it, up to you. There's a lot of fuzzy here. So, point of the lecture, what's GP, how do we do it, blah, blah, blah. So, genetic programming is briefly, it's basically a GA, except, like when you think of the GA, the examples we were looking at, and this is not always the case, but, you know, we looked at TSP. We looked at that silly example of optimizing, like maximizing the number of ones in a bit string. The graph coloring problem. We looked at n queens, which we could have represented as a one-dimensional array, but we also talked about the 2D array version. Like those are all valid GA representations. But with genetic programming, it's basically just a GA, but with a very specific idea in mind. The chromosomes, the candidate solutions, the things that we are encoding are going to be encoded as typically trees. Now, the specific types of trees up to you, depending on what you're trying to do. But they're typically, encoded as trees, but not necessarily, but this is the basic idea. And this really isn't that true of a statement, especially because sometimes it might feel like you're really splitting hairs between what's machine learning versus AI versus like, there's a fuzzy boundary. And it's not that GP, well that's the machine learning version of evolutionary computation, because you could use a GA for machine learning too. But a lot of times what we like to think of is, when we're optimizing TSP, we are optimizing the permutation, the order of the cities that we visit. With genetic programming, we're optimizing this tree structure that's typically going to represent a program. So we're optimizing a program for something. Yeah. And so it's the idea of programming via natural selection. And that's like a quote from Koza, who's the guy that invented it. I mean, here we're getting silly with our words. The representation's typically a tree structure. The recombination, which is just another fancy word for crossover, that's some idea of exchanging subtrees between trees. We'll see all examples of this shortly. Mutation, modify one of the subtrees. Selection is, typically we're going to do a fitness proportional one. And if you remember from the fitness lecture where I kind of went over all of those different ideas and said at the end of the day, just use tournament or maybe roulette wheel. So tournament or roulette wheel here is what you're going to want. And survivor selection, well, we don't really need to worry about it because typically it's going to be generational. But that's not to say you can't do a steady state version of GP, but almost always you see the generational where you take a whole population, you have the genetic operators may or may not be applied, we get the next population and repeat. So it's that more discrete version as opposed to modifying the one single pool. So this was developed in the late 80s, early 90s, but to be fair, it really is just a GA with a specific idea in mind. John Koza was the inventor, and an interesting story about him is one, he's always wearing the same red, white striped shirt. And two, his family actually got really rich for inventing the stuff that they put on scratch-off lottery tickets. So this guy was already rich, and then he just started playing around with genetic programming, evolutionary computation. And this also isn't quite right. It's in a similar niche of artificial neural networks, but that's not really right. Really, evolutionary computation in general falls under computational intelligence, which is in the same family as neural networks, but whatever. Typically, unlike your GAs, which very well could have gigantic populations, but typically with your GA, we're going to have huge populations. Very big, typically. It's typically way slow. If you're thinking of your GA, I don't know, who had like a population size of greater than 1,000 when they were running their GA? Raise your hand, let me know. No, not many people. All right. How about greater than 100 at least? Okay, well, okay, good. So let's say it was greater than 1,000. How many, did you have it run for more than 1,000 generations? Yeah, a bunch of people, yeah. So if you've got like 1,000 candidate solutions and you're running for 1,000 generations, if you kind of consider the runtime, how long did it take to evaluate like one generation? Probably pretty quick, right? Because if you're doing 1,000 of them, it takes 10 minutes, whatever. With GP, you'll have very large populations, but the fitness evaluation of these things are going to be slow for a couple of reasons that we'll talk about. But it's going to be really slow in comparison to what you might expect coming out of the TSP assignment. You're really going to want low mutation rates compared to other evolutionary computation things. Sometimes people don't even have a mutation in there. I usually do. And how much mutation you have will depend on a lot of things, like everything else in this course. These are just broad rule of thumbs. Rules of thumb or rule of thumbs?
Certainly not rule of thumbs.
Rule of thumbs? Whatever. So let's have a silly example. And this first example I'm going to show you is going to have multiple different types in it. And I'm just showing you this as an example to kind of show you where we're going, but then we're going to take a step back and go to symbolic regression, which is one-typed or non-typed, sometimes they call it. So let's say we've got this simple little problem. I'm pretty sure you can download the data set like this from the UCL machine learning repository. So let's say we've got a whole bunch of people and we want to evaluate whether or not they can get a loan or something. It's a silly little toy example. And the data I have on them is the number of children they have, what their salary is, maybe it's household, I don't know, if they're married, single, divorced, and then we've got this last column which is, do they get a loan or not? Should they get a loan or not? Should we give them approval or not? So, I don't know. You know, you look at this, your first thought might be like, yeah, we could use machine learning for that, right? Yeah. Great, so what should our model be? And here when I say the word model, I mean like what should that function be? And we could talk about different levels of abstraction when we talk about the function. We could talk about different machine learning strategies. We could talk about specifics within a type of machine learning strategy. The big question is, okay, well, what model do we want it to go for? What are we looking for here? Or pardon me, I know what we're looking for, but what should I use to help me find this solution? So here's an example. Maybe it's something like a decision tree. A simple decision tree. If the number of children is equal to 2 and their salary is greater than 80,000, then yeah, they can get a loan. Otherwise, false. Right? Very simple. So it's interesting though, because if we take a step back and think about TSP, we use the word search space a lot. And that kind of described all possible configurations for a candidate solution. And we want to search through all those possible configurations for the best one, or a really good one. And if you're having a hard time remembering that, remember we kind of showed it with that example in the genotype space for the bit string, right? Where we had, well, okay, from 1, 1, 1, 1, we can go to 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, and 1, 1, 1, 0. And then from here, we could go to 0, 0, 1, 1. We can go to 0, 1, 0, 1, and so on. Like we could draw every possible configuration, and maybe I'll draw an edge between them just if they're like having distance 1, just for simplicity. And I want to traverse this space of possibilities to find a really good one for the problem we're trying to solve, which in that case was maximizing the number of ones. Again, silly problem, but example. So that's the search space. The search space for this problem is all possible configurations of the zeros and ones. That represents that integer number we're maximizing. for TSP. It's all possible configurations of this all possible permutations of the numbers of cities. And we're moving through that space to find the best one, or a really good one that we're happy with. Here, though, you know, if my goal isn't to find like a solution, like a configuration of cities, a permutation of cities that gives me a good solution, right? If it's not that, where I'm looking through every possible permutation, here what I'm looking for is like all possible decision trees. The space that I'm looking through now, if we kind of think about like, well, how do I configure this? Well, the set of possibilities is the set of those like decision trees based on those values and based on some set of operators we care about. Yeah.
A question I have is, if you have a search space with a set of formulas, right, and eventually it just, with every new population, a new set of formulas is generated with the goal of trying to find the best one, how can you make it, or make sure that you're not accidentally generating like a bunch of formulas with syntax error, like with like.
We'll get there. We'll get there. And that's where it comes to the typed and untyped and all those fancy constraints and rules we'll talk about later in this lecture. So in this case, if I'm, like goodness will be a measure of like, well, how good is this classifier? In this metric, I don't know. I don't know how you'd measure goodness because I don't know how you'd validate the like, should you give them a loan or not, whatever. But we want, maybe this data was already analyzed by an expert and we want to create our machine learning algorithm to come up with a model that can replace that expert because they're expensive. So we'll just try to match what that expert said, and the closer that my model can match what that expert says, the happier I am. So there we go. This is my little decision tree. And I'm not even going to call it decision tree anymore. It's my little program. It's a simple one. If number of children is equal to 2 and the salary is greater than 80,000, then yeah, they're good. Otherwise, don't give them the loan. But I could represent this as that tree. And this isn't really a decision tree anymore. This is what we would call an S expression, a symbolic expression. It's a way to represent this program, this function, as this tree. Take a look, pardon me, my voice cracked. Take a look at what the leaf nodes are and what the interior nodes are. You'll notice that, so NOC, that's like a variable, that's a parameter. That is the number of children an individual has. Same with S, that's salary. S, that's a parameter. Every individual will have different values for that. That gets plugged into my function. And then I've got 2 and 80,000. Those are constants. But all of the things at the bottom are terminals. They're operands. They have a specific value. Some are literal values and some are variables. But the interior nodes are operators. They act on the operands. And I can kind of evaluate this up. So I could say, well, number of children is equal to 2, salary greater than 80,000. Those two things get evaluated to something. In this case, this is a number, this is a number, this is a number, this is a number. But if I ask the question, is S greater than 80, the answer's not a number anymore, it's a Boolean. Right? And same with if number of children is equal to 2, that's a Boolean expression. That's going to return true or false. And then at the very top, the root of the tree is an AND. And that's another operator that works on Booleans and gives you back a Boolean. So I can now kind of think of these programs as a tree. All right, so now we start getting into kind of what Matt here was asking. We've got this general idea here, but the question you're going to ask is, okay, great. We have our data set, and we know we have columns, like the values in there that are like number of children, salary, if they're married or divorced, whatever. We have these values, but how on earth, like, we have those values, but you're throwing in like equals, greater than, and what else should we include? Why did you include those ones? Could we have used divide, subtraction, multiplication? If, then, else? I mean, sky's the limit. We can define any other operator here we want that makes sense in the context, and maybe have it in our tree. So, number of children, okay, you have a sense of what the range of those values could be. 0 through, I don't know, something reasonable. It's not going to be like 1 million. No one's going to have 1 million children. Salary, again, you've got an idea of what the range is going to be. But like, you know, great, for 2 and 80,000, okay, you know, you've got that context there of what those values should be. But operators, like, does it make sense to use greater than? I think it does in this context, but I don't know. If we start to generalize, we're not going to have a sense of what operators to use. So this is where we define a language. So the language idea is probably the biggest new idea we throw in to the evolutionary computation. But it's not that bad, trust me. It's not trivial, but it's relatively simple. It's basically part of the constraints we apply to our chromosomes. Just like with TSP, we could have a string of, if we have n cities, I could have a string of random numbers between 0 and n minus 1, or 1 to n, whatever. But as we discussed, that's kind of a terrible representation. So we can apply this constraint where we say, okay, look, I realize you could be n to the n possible combinations, but it's going to be better because it's TSP. We want to visit each city once and only once. So maybe we'll constrain our candidate solutions to only be values, like unique values in a permutation. So we constrained it. Similarly with n queens, we constrained it such that we greatly reduced the search space, while also maintaining that we do include all possible valid and good configurations still. So we like that constraint, but there's that battle. With things like TSP, with these, like, again, toy problems in the context of evolutionary computation, interesting problems in and of themselves, but for evolutionary computation, we usually use them for learning and benchmarking. We have a good sense of things like the search space and whatnot, but once we start to go to, for example, like the problem I always talk about with like the symbolic regression, the fMRI stuff I did. What should, like, I want to put constraints on what types of things I can have as my candidate solutions such that I reduce the search space so it's not as hard as a problem. But I gotta be careful not to reduce it so much that I might eliminate good or the best possible configurations. If it's a problem that is well understood, we have a sense of what that is. But sometimes when we're solving problems where we don't know what the hell we're doing, that's a very difficult question to ask. So this is one of those things, it's that give and take, just like everything else in evolutionary computation. So what are the operators and operands we want to allow? So given the tree, we need to think about what the internal nodes and the leaves could be. If we go back, so now I'm kind of talking about non-typed or single-typed GP. Non-typed, single-type, it's the same thing. It means that we don't need to deal with different types popping up. In the previous example, we had different types in our tree. We had number values, and we had Booleans as well. In this example, it's just numbers. So based on what you saw, the S expressions, what does this represent? What does this tree represent? Well, it's 1.2 minus x times y. It's arbitrary. It's not that meaningful, but that's what it represents. X and y, presumably here, would be parameters for that function. So you would think, like, okay, well, if this is a function, a program, whatever, I would say, like, okay, f of x and y equals 1.2 minus x times y. Great. There. So that's what this is like representing here. So, symbolic regression. Now we're stepping in, we are really focusing on the single type. And then we'll talk about the typed as we go. Because the single typed is, I don't want to say easier, because it doesn't mean, like symbolic regression, is not an easy problem. It's just easier to learn about genetic programming when you don't need to worry about all the extra constraints of like making sure the types line up. So if we're doing symbolic regression, the operators that we might want to use are things that make sense in the context of numbers. Operations we can do on our numbers that give us back a number that would be reasonable in this space that we're dealing with. So maybe I've got some operators like addition that takes two operands and gives you back one number. Subtraction, multiplication, division. Although we gotta be careful about division, we gotta be worried about divide by zero. We'll come to that. Then we also have things like cos, maybe other trig things in there, ln, e, powers of, that might take one value and return another one value. But we can have these operators that work on numbers. Yeah?
Does it matter what kind of traversal you use when you traverse the trees? Like, does it matter if you use in order, pre-order, sort of?
This, you're going to want to do, we'll come back. We'll come back. We'll come back to this because it's an interesting question that you're asking. So he was asking, like, okay, if I've got a tree, how do we evaluate this? Like in order, post order, whatever. Usually what you're going to do is like a depth first recursive analysis of this. The trouble is, what do we all know about recursion compared to an iterative thing in your computer? That's possible, but hopefully not with the numbers we're dealing with. Come on. What's terrible about recursion? It's slow on these computational systems. It's a lot slower because the extra overhead with creating call frames, pushing on the system stack and all that. Where if there's an iterative version, it's fine. But what do we also know about modern compilers? Come on, I talk about this in 162. I know you know this.
That was 3 years ago.
All right, fine.
I mean, I wasn't there and I can guess what it is.
What do you guess?
The compiler would probably convert it to some iterative version anyway.
So a lot of this is going to be tail end recursion. Raise your hand if you've heard that word before. A couple people. It's a fancy way of saying it's kind of easy to convert it to an iterative version. So a lot of modern compilers will, before it turns it into the actual machine code or byte code, whatever language you're using, will convert it to the iterative one because it knows it's a little faster, there's less overhead. But do note that that overhead of recursion is a consequence of how these computational systems work. There are other computational systems that exist in this universe that are not bogged down by that. One example would be humans. If I give you guys a recursive algorithm to execute, you could do it without having to create call stacks and everything. But anyways, let's not worry about that. That's getting into the weeds of other things. All right, and then what operands do we want? We've got our operators. What operands do we want? Probably some constants and variables. So x and y are like the variables. These are the examples of like, okay, should this person get the loan? Well, what is their x and what is their y? Plug it in, what's the answer? Should the next person get their loan? Plug in their x and y. But we also have the constants, which are just there. So what does this one evaluate to? Well, do I have it? No. 1.2 minus x plus the sine of 1.2 minus x times y times e to the x. Why? Just because, again, arbitrary. I will perhaps take a moment. Is there anything interesting you see in this tree? I mean, there's no right answer, but there's something I'm kind of looking for. Does anyone see anything in this tree that you go like, huh? What do you see?
The different number of nodes on the left and right subtree.
Okay, that's not what I was looking for, but that is a good observation, and we will talk about that idea soonish. Anything else you see? What do you see?
E to the power of an x.
E to the power, yeah, that's a good one too. That's not what I'm looking for. And what were you going to say?
So the variables and constants must be the listed leaves in the...
Yes, that is a good observation, but not what I'm looking for. But by the way, these are all very good observations, actually. Now you've ruined my question. Yeah.
I mean, it's the same as what he said. My bad, I didn't know. But you see 1.2 minus x twice.
Yes, that's what I was looking for. There's 1.2 minus x twice. That's interesting. But we'll put a pin in that and come back to that a little later. Yeah.
I have a question to build off of the person who made the comment saying that it's like uneven on both sides.
Yeah.
If you were to balance this tree, would it improve? Would it break or improve? Would it break it or would it improve the computational complexity?
You'd have to be careful. How would you balance that tree?
I don't remember.
So that's an interesting observation. It might work in certain cases, but here we're going to be in trouble because as soon as we start to balance it, we might actually change like the order that the operations take place in.
My instinct is that because of the sign.
The sign kind of throws it off.
It almost guarantees you probably can't balance it without some weird stuff.
Now, but if we had it such that all of our operators kind of followed the same, what are the name of those fancy math rules? Distributive, commutative, and whatever. Whatever the fancy name for the math rules, if they applied to the certain set of operators we were using, we could rebalance it. It wouldn't matter because you know how like there's some operations where it doesn't matter the order that you do them in?
Oh, I know.
Like if you multiply A and B together and then multiply it with C, it's the same thing as multiplying B and C and then multiplying with A. Doesn't matter. So in there are certain cases where balancing would be fine, but as soon as you throw an addition in there, you got to be careful. Neat point, however. And that does tie back with exactly what Liam was asking about, with like, well, you know, it's really uneven. This is really good observation. So, that was untyped, or one-typed, because they were all numbers. All the values were numbers, and all the operators worked on numbers and gave you back a number. But we can talk about different types of problems where we have more than one type, like that example of the lone one. So we might have mathematical operators, and maybe we want if and greater than, less than, equal to, and, or. So we've got numbers, we've got the mathematical operators we just talked about, but we've thrown in Boolean ones. The operands could be constants and variables, but the constants now, like the variables, will include different types. It could be a length, and then what's the red? I guess it's from a set of specific types. I guess maybe red is like Boolean. Is it red? I don't know. It's arbitrary, it doesn't really matter. It's just an example, but the point is, as soon as we have different types, we gotta be careful, because if I only allow numbers as constants, it might kind of be hard for the tree to be generated if it doesn't have the ability to have Booleans in it. So we might need constants of Booleans. And the types of our variables will be numbers and Booleans as well. But this tree here is valid. Because, okay, we've got two numbers, presumably length is a number. If length is less than 5.2, or it's not red, then something, whatever it means. Maybe it's classifying, I don't know. If it's a small ant, that's red. Whatever, it's a silly example, that's all that matters. But this tree, we can interpret as a function, a program. So other cases, we might want, okay, if, greater than, less than, equal to, and, or, operands. Here's another example with a little bit more in there. We threw in an if. I think in the last one I actually listed if as well, but we didn't, yeah I did, but we didn't include if. So now you'll notice that, I mean, all the other trees we're looking at were like binary trees. Kind of, because they were binary trees, but some of the operators would only ever have one child anyways, so, you know. Here it's a little different because we have like an if, which might have two outcomes. So now we can represent a program like this as a tree. And maybe this one here is programming a robot how to traverse a maze full of food. I don't know. Again, a silly little example. But the program could be, okay, if food exists forward and food does not exist to my right, move forward. Otherwise, turn right. Now in this case, it's kind of giving me back an instruction with the if or the turn right, but you can imagine that those are more programs. If that's the case, evaluate this other Boolean expression that might return true or false to tell you if you give them a load or not. Yeah?
How did you know that true evaluated to move forward and false evaluated to turn right? How do you know it's not the opposite?
How do I know? Because this is the arbitrary example that I'm showing you.
Okay.
In the encoding that you actually use in your code, it wouldn't be ambiguous. All right, great. So, language. Language is the wrench that gets thrown in that's the most differentness compared to what we've seen. But really all it is a set of rules we are describing to constrain the search space, like all of the other things we saw with the GA, but with this type of thing, we like to get like explicit with our language. We define a GP language. The GP language is what are the operators and operands that are allowed in our functions, in our programs. Okay, up until this point, it's all high-level talk. We're going to get to some examples. But now if we want to throw this in to evolutionary computation, like everything else in the course, remember slide 1, day 1? I showed you the whole course on one slide. Remember that? It's that loop. Initialize. Evaluate, select parents, genetic operators, evaluate, select parents, genetic operators, repeat, 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 repeat until you're done. That right there. Now we just need to use that for our new special encoding for these trees. So, I don't know, we could just randomly generate trees that are valid syntax-wise, type-wise. So randomly generate trees such that the children work with the operators. But this could be problematic given that, like, we've got, you know, when you think about that TSP example, even in the constrained example, where we constrain the search space to like n factorial minus 1 divided by 2, but we've got that huge search space, right? It's at least finite. There is a fixed finite number of possible configurations. Here, with our trees, it's technically infinite. It could go on forever. There's nothing theoretically stopping it from doing like plus 1 plus 1 plus 1 plus. It could go on forever. So it's a huge search space, but it's worse, right? Because it actually could just keep getting bigger and bigger and bigger. So that's something we have to keep in mind, and relates back to what Liam kind of pointed out, and what Matt also noticed too. So an easy fix for this though, like any good computer scientist, find a lazy solution, set a max depth. Great. Well, how deep should you let it be? Well, that's tricky, because that's another constraint we put on our candidate solutions. If we have a max depth of like 3, okay, well think about if we had a tree that was just full of binary values, how many possible nodes is that? How complex of a program could it be? Maybe we should make it depth 5. Well, the programs are suddenly a lot more complex, but is it enough to actually like, could I represent a function, a program, as a binary tree of depth 5 that's sufficiently good for the problem I'm looking at? I don't know. Maybe I need to make it deeper. I don't know. Like everything else in evolutionary computation, the answer is, but remember, we're applying these algorithms, these ideas to problems that we don't have other good ideas for. So the answer is always going to be regardless of the algorithm you use. If you're dealing with a toy problem that we have a really good understanding of, yeah, you might have a great sense of like, okay, well, I really don't need to make it any deeper than this, because I know that the function to generate the data I gave you was only like 4 lines, like it was only like 4 operators deep. So, you know, you're probably fine having a max depth of like 3 or 4. But in reality, you don't know. I might have made my functions I gave you in those text files for assignment 2 have like 1,000 operators in it. So how deep should you make your tree? You don't know. If the tree gets too deep, maybe it's at risk of overfitting. Maybe it gets way worse at getting overfit. Shoot, we're running out of time. Full, when we initialize, if we set a max depth, maybe I want a full tree. Yeah?
Could you have a GA like wrapped around some sort of a GP to like figure out? Well, I guess, I mean, you already mentioned that actually classes ago that you can use a GA to tune parameters.
Yeah, it's like meta. People will use a GP to make GPs. It's called like meta genetic programming. And then why not have a GP make the GP that makes the GP? Well, yeah.
And then rabbit hole.
Exactly. And then well, you're in trouble.
Yeah.
The GP itself is already kind of meta.
You're right, it is, right? And again, like everything else, the answer is to a lot of these questions is, yep. Try it, see what happens. That's the best answer.
More depth.
More depth. Although, there's going to be a point where you go like, nah, I'm okay. Okay, there are two strategies for initializing. There's full, make full complete trees where internal nodes are operators and leaves are operands. Great, that's where we start. I mean, once evolution takes place, the trees can grow in depth. But when we generate the trees to start, maybe that's our strategy. Or maybe we do grow, where you randomly generate the trees by starting with an operand, and then pick either, roll the dice and randomly select an operator or another operand. And if it's an operator, great, that's a leaf node. Go over to here and then keep going. You can grow, you can do full. The strategy that most people do is called ramped half and half, which is basically you do a little bit of both. Long story short and deep, there's a line of code that you say initialize, ramped half and half. Boom, done. You're doing what everybody does in genetic programming. So to be clear, I'm running out of whiteboard space, and that's really not an eraser. The grow is you pick an operator and you go, okay, great. It needs 2 leaves, or two children. And then you roll the dice and you select minus. Over here you roll the dice and you get a 2. Well, that's a leaf. There's nowhere to go from there. And then, okay, so here we get x. And then here you get multiply. And that's grow. Full is where you just ensure that if I want it to be depth 5, I'll go to the bottom and be like, okay, you're going to be all operands, whether it's a constant or a variable, and then fill in operators as you go. Ramped half and half, you do a little bit of both. This is what everybody does if you're using a tree representation for your genetic program. Selection, conventional selection strategies can be problematic with huge populations. So this goes to what I was saying at the beginning. Because with genetic programming, typically you want gigantic populations. Way bigger than what you would typically have for your GA. The answer to why really is more of an empirical answer where it's because it just works better. We could get into the weeds of talking about why and trying to get an intuition. But a lot of times in this world, like everything else, it's empirical questions with empirical answers. Just try. See what happens. There's ideas called over-selection, split 2 populations into 2 groups, and then you take the top percentage. All these fancy things. At the end of the day, the catch-all tournament selection. The catch-all tournament selection or round robin, you're always good. That's what everybody's using. And that's what is default in deep, which I'm recommending you use, but of course you don't need to use deep for assignment 2. You can use whatever other GP system you want. Genetic operators, well, classically, you're going to want a higher crossover rate, but crossover tends to be very destructive when working with trees. And we'll show some examples of this as we go. And because it's destructive, and remember, destructive is a relative term, because it's destructive, it also kind of serves the purpose of mutation as well, because you kind of remember how with crossover, once the population starts to converge a little bit, crossover isn't really good at adding new information into the population. It's just good at transferring the information around the population. Or mutation is good at kind of throwing something new in there and maybe it takes off. So because crossover can be fairly destructive, and because the search space is so huge, infinitely so, these crossovers can end up having wild implications. So that's why we can get away, classically speaking, with lower mutation rates and just sticking with crossover. Some people don't even use mutation. But this is classically, this is rule of thumb, and this is assuming you're using a tree representation. We'll probably talk about another representation a little later. No mutation. But usually people use mutation these days just with a small number, but mutation's easy to do. Sorry, say that again.
There's no need for mutation for the genetic code.
So a lot of people, you don't need to, and it'll still probably
But
work.
A lot of examples say the very low number of mutation.
So what people, so if you go to like Koza's original books from the 90s, it's like all just crossover. Since then, people will throw in a mutation, but it's a very low chance of it. So that's what it is. But again, asterisks, like everything else. Yeah,
Would a crossover in this case be kind of like reversing a trait?
just sit tight. Good questions, but sure. You can do whatever you want, really. Only ever apply one or the other, not required, do what you want, whatever. So, crossover. Here's an example. Pick two subtrees. This is an example where it's singly typed, symbolic regression. Pick two subtrees. How? Just pick two nodes. Maybe it's a leaf node. Maybe it's not a leaf node. Pick them, and then swap them. See? I've got x minus 5 plus x, and then I'm crossing it over with x times x plus 2. And so I replace the 5 with that subtree. And similarly over here, I replace it with the 5. So crossover. Easy peasy. Any questions about that? That's your typical one, but you could do whatever you want, like you were suggesting.
Well, it's just I wasn't sure because it would only be one trait. 'Cause you'd be-
Well, then maybe that'd be more of a mutation, I guess. Any questions about that? Now, if I ask you though, what if it was typed? You'd probably go like, well, okay, it gets a little bit more complicated because I can't just randomly pick two subtrees. I need to make sure that the subtrees I pick produce the same types such that I can do the crossover. Because imagine I did a crossover with something asking like, is 5 less than 7, right? But over here I'm doing something that's like not blue. And I do the crossover, and then it's going to be not blue less than 7. Well, that doesn't make sense, right? We're now mixing the types. You can't take a Boolean and ask if it's less than 7, unless it's C++, and of course you can. So you got to be a little bit more careful when it's typed, but it's not too bad. There are different strategies for it, and it's actually kind of a, you had to be there, but it was a funny story, I promise. Back when I was learning GP, it was like fourth year undergrad, the popular GP system was called ECJ, I think. It's a Java-based one. And it kind of had these like default settings. And the default setting, when you did typed GP, was randomly select two trees and do the crossover, but if they're the wrong type, just skip it. But we didn't know that, and so like all of our results were absolutely terrible until someone read the documentation, like you should, and was like, well, if you want this, you can increase the number of times it tries or something to improve it. Remember, like the joke is, 5 hours of coding and debugging can save you 5 seconds of reading the documentation. But anyways, that's type GP throws it off a bit. And then of course mutation, well, pick a subtree and replace it with something else. Here I picked X, I replaced it with 7. I mean, here it was a terminal with a terminal. They were both leaf nodes, but there's nothing saying it needs to be a leaf node. I could say replace it with, like here I just picked a random thing. I could also pick an operator and then maybe try that grow strategy to also like make it not just a terminal, but like another subtree or something. Totally doable. And there we go. All right, and then the next thing we're going to talk about is BLOAT, which is what Liam and Matt were talking about. And it's talked about in the, what's it called? The GP Traveler's Handbook Guide, whatever the text is for the course. They call it Survival of the Fattest, which is silly. But anyways, that's that.